Sudo make me a sandwich. Can you read the flag? I think you can. Additional details will be available after launching your challenge instance. Right, so now we're going to go through the notes from the challenge that we just did. So initially what you want to do is you want to check the permissions that are available. So we use list-la to check file ownership and permissions, e.g. from what we just did, we found out that users such as ourselves had no privileges. Next, what we did was we checked our sudo rights using sudo-l to see which commands can be run with root privileges. And a tip is to look for all no password entries. Bypassing restrictions. If a common command like cat is restricted, you want to look for alternative binaries in the sudo-l output. Emacs escape. If Emacs has sudo rights, use sudo emacs-nw file to read restricted files like flag.txt. And we know that -nw stands for no window, which forces Emacs to open directly in the terminal rather than trying to open a new graphical user interface window, which would fail in this web shell. To exit Emacs, you do Control-X followed by Control-C. Resources, GTFOBins, a curated list of Unix binaries used to bypass local security restrictions. Always check this when a specific binary is allowed in SudoOS. That's that challenge done. Time to move on to the next challenge, Quizploit. Solve this quiz. Download the source code to answer questions here. Download the binary to answer questions here. Additional details will be available after launching instance. ELF binary analysis and protections. ELF stands for executable and linkable format. Binary characteristics. When starting any binary exploitation, PWN challenge, the first step is enumeration, gathering data about the target file. So the architecture, 32-bit versus 64-bit, affects register sizes and memory addresses. To find this out, you use file and then that binary file. Linking. So if it's dynamic, it uses shared libraries. Static libraries are baked into the file. Stripped, debug info removed, and not stripped, function names / addresses are visible. And you use nm and then the binary file name. Security mitigations. Modern compilers include shields to prevent exploitation. We check these using checksec. NX, no execute, marks the stack as non-executable. Executable. You cannot run shell code directly from a buffer. PIE, position independent executable. Randomizes the base address of the binary in memory every time it runs. Vulnerability, stack-based buffer overflow. The vulnerability occurred because the program's input limit was significantly higher than the allocated memory space. The math, so buffer size was 0 times 15, which is hexadecimal, which is 21 bytes. To figure it out, you look at the first digit of 15, which is 1, and you do 1 times 16, which is 16, and then you add the next unit, which is 5, so it'd be 21. The same process applies with 90, so 9 times 16 is 144, plus with 0 is still 144. And to find the overflow capacity, you do 144 minus 21, which is equal to 123 bytes. By providing more than 21 bytes, you can overwrite the save frame pointer and the return address, RET. Exploitation techniques. Ret to win, return to win. This is the specific technique used in the challenge. Since a win function existed at a static address, you only needed to overwrite the return address on the stack with that hex value. The result, when the main function finishes, the CPU returns straight into the win function, executing the code that prints a flag. Return-oriented programming. Since NX was enabled, we couldn't just write our own code. ROP is a solution for bypassing NX. How it works, you find a tiny snippet of existing executable code called gadgets that end in a ret instruction. You string these addresses together on the stack to perform complex actions like calling system functions. Perfect. So that's that challenge done. Go on to the next challenge, which is StegoRSA. A message has been encrypted using RSA. The public key is gone, but someone might have been careless with the private key. Can you recover it and decrypt the message? just to recap over what we've done. StegoRSA challenge, so metadata analysis. Concept: metadata is data about data. It includes file properties like camera settings, GPS coordinates, and comments. Investigation: use Exiftool to inspect file headers and metadata fields. Indicator: long repetitive strings in the comment field, such as sequences starting with 2D, 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 etc., often represent encoded text or keys. Decoding: hex to ASCII. Concept: hexadecimal base 16 is a common way to represent binary data in text format. Pattern recognition: the hex sequence 2D represents the ASCII character dash. An RSA key header is dash 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 begin. Starts with 5 dashes, appears in hex as 2D, 2D, etc. Command line utility: use XXD to convert plain hex strings back into their original file format. For example, echo hex string, so obviously you'd replace that with that, and then you go XXD after the separator, -R -P to a private underscore key dot PEM. R is replaced, P is plain text, .pem is just a file. RSA decryption. RSA is an asymmetric encryption algorithm. Data encrypted with a public key can only be decrypted using the corresponding private key. I'm probably going to do a theory video on that, so just stay tuned. Key identification. A valid RSA private key is typically stored in a .pem file and includes specific headers. Decryption tool. Use OpenSSL to apply the private key to an encrypted ciphertext file. Here is the example. And then you would change flag.enc to whatever the flag file is. Critical takeaway: security through obscurity. Hiding sensitive information like a private key in image metadata is a weak security practice. It relies on the attacker not knowing where to look rather than actual cryptographic strength. Key management. Private keys must remain confidential. Storing them in an unencrypted or easily decodable format, even within another file, compromises the entire encryption chain. Common steganography tools and methods. Well, just to begin, steganography is the practice of representing information within another message or physical object in such a manner that the presence of the concealed information would not be evident to an unsuspecting person. So in this example, it was the image file. So metadata, to find that, you'd use Exiftool, checks for hidden strings in file headers. Embedded files, you'd use binwalk to detect and extract files appended to the end of images. Strings, you'd use the command strings and to find human readable text hidden in binary files. And then pixel hiding, you'd use steghide, extracts data embedded within the pixels of JPG/BMP files. Thank you very much. That's everything for today. I'll catch you tomorrow